Today we will get started with distributed systems. We will understand transparency in distributed systems, the notion of time, clock drifts, and time synchronization. And we will finally understand Lamport Logical clocks. One of my favorite quotes about distributed systems is that of Leslie Lamport. He says that a distributed system is one in which the failure of a computer you did not even know existed can render your own computer unusable. And in today's lesson, we will try to understand what he meant by that. A distributed system is a computing environment in which multiple computers coordinate with each other by passing messages to achieve a common goal faster. Distributed systems are faster than the traditional method of computing in one single node, or in other words, one single computer or machine. That's because you have more computing power, because you have more machines, but they are harder to maintain. They offer an abstraction of the underlying distribution of the task, in that it will appear to a normal user as if he is using only one computer. For example, when you use the internet, everything is abstracted away from you. All of that complexity of taking a message and passing it from one network into another until it reaches the destination, and all of that data encapsulation, all of that doesn't appear to a normal user. It just appears that all of that computation is done in his end computer, in his own computer. In other words, from this perspective of a normal user, he is ignorant of the fact that in order for the internet to work, it requires more than one machine. He just thinks that all of that computation is done locally. So that's what we mean by a distributed system offers an abstraction. Everything is abstracted away. In order for a distributed system to appear like one single component instead of multiple components working together, it needs to have transparency in the following aspects. First of all, access transparency. We just mean by that to hide differences of data representation. That's because in a distributed systems, we have multiple machines working together with each other. And some machines use different architectures, which means that the data representation could be different. A good distributed system will hide that difference, and it will make it look like all of those machines use one single architecture. So there is only one data representation. It needs to have location transparency. You need to hide where a resource is located. And migration transparency, which means hide that a resource may move to another location, also called relocation in the case resource is moved while in use. It needs to have replication transparency. We hide that a resource is replicated or could be replicated. And concurrency transparency, hide that a resource is shared by multiple competitive users. And failure transparency, we hide the failure and recovery of some resource. The biggest problem when it comes to time in distributed systems is the impossibility of trying to synchronize all computer clocks to agree on the current time. That's because obviously all computers tell time by using a clock. Each computer clock is a form of a microchip that has a crystal quartz inside it. We apply some electricity to this crystal quartz so it starts vibrating. The shortest time any computer could tell is one vibration. But the problem is that not all computers have exactly the same crystal quartz, so they might differ in their temperature, or they might even differ in the angle at which they were cut. So it's not a perfect cut where they all have exactly the same size. These differences will affect the frequency of their vibration. So they will have different frequencies, and the difference in frequencies will make time differ from one computer to another. In short periods, you won't notice the effects, but that difference in oscillation or vibration will accumulate over time, and it will make a huge difference. So the difference between the rate of oscillation from one computer to another is what we call the clock drift. So let's say we have a simple system composed of three computers or three processes. So each process running on a different computer. Let's say that we manage to synchronize their clocks and all of them have the value of 8 o'clock. So they agree to start exchanging messages with each other after half an hour. What happens is that some processes will reach 8:30 before others due to the difference of the rate of oscillation of their internal clocks. For example, process P1 will reach the value 8:30 and start exchanging messages as promised before P2 and P3. So start sending some messages. But P2 and P3 would be very confused. For example, P2 would have the value of 8:10 and P3 would receive this message at 8:20. Both of them are confused. They're like, we didn't agree to start exchanging messages at 8:10. But process P1 reached 8:30 before these processes did due to the difference of the rate of oscillation. So it's all because of the clock drift. And then P2 reached 8:30 before P3, so it starts sending. But then, of course, P1 would say, we are actually at 9 o'clock, so you are late by half an hour. And in this one, he says, well, it's not actually 8:30, it's 8:25, for example. And then P3 starts sending messages, and then process 1 would go insane. He was like, man, you are 2 hours late. This is, we are at 10:30, for example. And process P2 starts bragging about process P3 starting exchanging messages late by half an hour. So this is 9 o'clock. So as you can see, even if they started at exactly the same value, their clocks drifted and they have now different values. Trying to rely only on these physical clocks to order events generated by a distributed system is impossible. Let me explain by an example. If our distributed system generated three events, E1, E2, and E3, each event represents the creation of some message at a certain point in time. But P1, P2, and P3 have different clock values due to their clock drift. So M1 is created at 9:30 from the perspective of P1, and M2 is created at 8 o'clock from the perspective of P2. M3 is created at 7 o'clock from the perspective of P3. Then they start exchanging these messages. Each message is coupled with the timestamp of its creation time. P1 receives the message M2 before M3 at 10 o'clock and M3 at 11 o'clock. P2 receives M1 at 8:30 before M3 at 9. And P3 receives M2 at 7:30 before M1 at 10 o'clock. The problem is trying to order these messages by their creation time and know which was created before the other. It is actually an impossible task. One way of trying to solve this is by using their timestamps. So we can use the timestamps that are coupled with these messages to try to order these messages. But due to the clock drift, why would any process rely on other process clock? Each process thinks he has the correct clock value from his perspective. So they can't actually trust the timestamp that has been sent with the message to actually order these messages. Another way is to rely on the delivery time to actually order these messages. That wouldn't also work because from the perspective of P1, he thinks that event E1 happened first and then E2 and then E3. But from the perspective of E2, he says, no, you got that wrong. It's actually E2 and then E1 and then E3. From the perspective of P3, he thinks both are wrong and he is correct. He says, you got it both wrong. It's actually E3 and then E2 and then E1. Let's say for the sake of simplicity, the actual order is what we are seeing, which is this one. So for the sake of simplicity, we will say that E1 happened first and then E3 and then E2. None of these processes got the correct order. And even if we delay the receival of M2 to actually get the correct order from P1 to actually get the correct answer, P1 has no way of actually proving that that's the correct order. So total ordering is impossible in distributed systems. The point is, trivial tasks like ordering messages in one machine is very easy, but it is a nightmare in distributed systems. In order to solve the problem of time in distributed systems, Leslie Lamport partially solved it using a very clever technique that is intuitive to human reasoning, which is the concept of causality. Lamport noticed that causality necessitates the notion of time. Each cause C and its effect E, C must have happened before its effect E. Let me give you an example. If a person pushed a glass of water and it got broken, it is objectively true that pushing the glass must have happened before the glass got broken. So if we have the following set of events happening in our system, let's say that P2 says that in order for him to start executing event B, he needs to first wait for event A to happen. So event A is causing event B to happen. So it is actively waiting until event A starts existing. So unless event A exists, event B wouldn't exist, which means that event A must have happened before event B. And P1 sends the message coupled with a timestamp with his own clock value, which is, for example, let's say 60. So if event A must have happened before event B, a quick trick would be to update the clock of P2 and to make it 60 plus 1. Since event A must have happened before event B, that means I can safely update my clock value from whatever it is to 60 plus 1. So event B is the effect and event A is its cause. So event A caused the existence of event B. And then event B is causing event C, which means event A obviously happened before event C. And then if event C caused event E, it means that B must have happened before event E. So whenever we have a causal path, so we call this a causal path, we can actually have some degree of ordering of messages. That's because, as we said, causes must precede their effects. But in this case, we have event D. We can't actually know if event D happened before A or B or C. That's because there is no causal path between A, B, C, and D. All we know is that event D must have happened before event E. from the perspective of P3.